Good afternoon. Thanks for having me today. So today my topic will be on optimistic privacy preserving AI. We actually have a very fun abbreviation of it, which I'll show you later. But first of all, I just want to sort of gauge the audience. So how many of you have heard of ZK, zero knowledge? Okay. How about zkML, zero knowledge machine learning? Okay, much less. So I'll take a little bit of time introducing what is zkML, because that's actually a very important background before I proceed to my research. But basically, it's a natural progression of having gone from a CK system to an optimistic system to the research that I'm going to present today. Right, so zero knowledge machine learning. So for those of you who already know what ZKP or zero knowledge proof is essentially saying that we want to put some computation into a cryptographic proof to prove that you have done so, right, without actually rerunning the computation. So to reapply that onto machine learning is actually saying that, okay, let's say I make a prediction on stable diffusion, right? I put a prompt in, I get an image out, and I put this whole process into a zero knowledge proof. Right, so for those of you who already know what a zero knowledge proof is, you probably think that that's going to be very, very expensive. And that's true, right? But there are two reasons, at least, why people are trying to tackle it or solve it with ZK. Right, so first of all, by putting this whole process of machine learning into ZK, you can gain verifiability. Essentially, you can tell people that, hey, you can verify that I have done so without rerunning the whole computation. And with ZK, there's also sort of two promises, which is, first of all, input privacy, and second of all, model privacy. However, you see that I put an asterisk around those two items, right? So I put a little asterisk, which usually means precaution. So there is something that you should be aware when we talk about privacy with ZK machine learning. And then the known issues is just all the known issues that is the same with ZKP, which is it's very memory consuming, it's very time consuming, right? So right now we can only do zkML for a very small network. And by very small, I mean something that you're usually only using for benchmarking, right? So it's small in the sense that not even for like real life use case, at least for now. So let's tackle what I put in asterisk one by one. So usually, we assume that if we put things in a ZKP, if we put things in a zero knowledge proof, and then we hide the input, then everything is private, right? Normally, that's the case, but with machine learning, it's tricky. Because with machine learning, there are actually a lot of data or a lot of statistics that you can gain out of the output. Right? So yes, I cannot get the input directly from the ZK proof itself, but I can actually get the input by knowing a lot of things about your machine learning network. Right? So actually, so a few things to beware of input privacy is that, well, when we say input privacy with ZKP, we are talking about doing the computation on client side, so on the client's device. So essentially, that means that we are handing over our machine learning model to the user. And that means that the user can actually do whatever they want with the model privately and locally, right? So one thing that they can do is actually run this local model over and over and over again to train their own model to reverse the computation that is being done. Okay, so essentially, let's say maybe an image would be more interesting. So this is like a data set that people usually use for face recognition. And the top row is actually the original image. Okay? What we have done here with the bottom row is we feed these top row of image into a neural network that is supposed to like shuffle things around, mix all the data up until it's not something that is the image, right? And we feed this into a model, and then we take that result, we try to train like the reverse. And that the bottom part is the result of our training. So essentially it's saying that if you are giving this model, just handing it out for free, people can actually use this model to train whatever inverse model that takes to break the privacy of your input, right? So given some data and the model, I can actually train a inverse model to always reconstruct the image. So the bottom row is what is being reconstructed. Right, so you can actually see that input privacy might not be a case for zkML specifically because of the very nature of machine learning. Well, what about the other promise of zkML, right? Which is, well, okay, we can't hide the input, sure, but we can hide the model, right? We can put the model into private signals and then hide the model. So there's actually a lot of problem with this model privacy promise. So first of all, if the model is private, essentially you're saying that only one single entity can be able to be the prover. Right? So because you want to keep the model private, so that means that only the model provider or the company that is providing the model is going to have that access to that data. Everyone else is just going to trust that single prover for them to provide the service. And actually, this is exactly the case with Web 2, right? So right now with Web 2 API, it's almost the same thing. You are trusting OpenAI to give you the result. You're trusting whatever company, Web 2 company, the server, the API to give you the result, right? And actually, even the Web 2 company is aware of the danger of this. Okay, so models like GPT is fine because it has billions and billions of parameters. So people who have access to these results, like these APIs, they are never going to reconstruct the same model. But let's say if we're only doing very small model, right, like thousands of parameters or 10,000s of parameters, essentially what one can do is, well, I will make more inferences than the parameters that you have in your model. Right? So it's a degree of freedom for those who are familiar with statistics. Right? As long as I make enough inferences, I can basically infer all the parameters in your model. And that actually breaks the model privacy. Right? So that means that even with zkML, what will happen is as your service lasts, as you provide more and more service, more and more samples for people to train this model, they can essentially reconstruct this model, what we call usually a heuristic model, right? So they can reconstruct a model, train a model that acts very similar to yours. So actually, model privacy is also not really a guarantee from zkML. And hence, actually, there's still some part of crypto economics that needs to be done if you want to have model privacy, right? So something like scarcity. For example, if you're doing a AI NFT collection that only has, I don't know, 1,000 NFT or 10,000 supply, then should be fine, right? Because your model size is much, much bigger than the collection size. So you won't be worried about people being able to copy your model over just by the 10,000 samples that they have. So a lot of these sort of promise doesn't come with ZK itself, but also with crypto economics. Right, so that's all I'm going to talk about zkML, since we still have 2 parts to go. But the bottom line is that if we're talking about machine learning and verifiable machine learning, ZK alone is not enough. Okay, so we need to align with the economics. So the other primitive that I need to go through before I really get into optimistic privacy-preserving AI is a research initiative that we have started at ORA. So basically, optimistic machine learning. So I'm pretty sure everyone has heard of like CK rollup and OP rollup, right? So it's funny because we started with OP rollup and then we move on to CK rollup, right, with better security guarantee. And in the machine learning world, we actually did the opposite. We start with zkML, right? People thought that, okay, just do ZK with machine learning, we can get a lot of guarantee. And then at Aura, we think, well, why can't we do optimistic machine learning? Right? Why can't we borrow the same thing from optimistic rollup into machine learning. So that's what we have kind of proposed and invented. Right? So we have proposed, well, if we merge game theory plus machine learning plus blockchain, we get optimistic machine learning. So essentially, it's the exact same thing with optimistic rollup, where we can have interactive fraud proofs. We can have on-chain arbitration of the different submitter and validators trying to submit like different machine learning results. And in our particular design, we can also separate execution from proving. And this is an especially important efficiency gain that we have. Because in zkML, you cannot separate execution from proving. Essentially, you have to prove the whole thing, and that is easily 1,000 or even more times of overhead. Right? But if we can do separate execution from proving in an optimistic system, there's essentially no overhead when you first run the machine learning. So the computational efficiency is exactly the same as if you run it in so-called Web 2 way. Until there is someone else who wants to disprove your result or challenge it. Then you go into sort of the fraud-proof system. Right, so why would we want that? We want that because, well, first of all, zkML isn't really production ready for real-life models that we want to use. So, well, with OPML, with optimistic machine learning, it's at least 1,000 times cheaper than zkML. It also only takes so it's an any trust assumption, meaning it only takes one out of your whole network to be an honest verifier or an honest node in order to maintain your network, to keep your network running. Right, so as long as there's one node in your network that is being honest, then you can always assume them to be submitting a correct result for your machine learning inference. So that's why we want OPML. And currently, we already have Stable Diffusion and also Llama. So these are models that other sort of verifiable machine learning scheme would never imagine being able to run. So this is sort of the unique advantage of OPML. Right, so before I talk about our new research initiative, this is like a very basic comparison of OPML and zkML. So just to recap, basically, OPML, the only thing I guess the OPML doesn't have compared to zkML is the privacy guarantee. So that's on the left end of the slide. But what we gain is actually computation efficiency, right? So in OPML, we can do native execution with cost that is around the same as Web 2. You can also delay the proof generation, right? Meaning you don't need to generate any proof if there's no challenge. But then in zkML, like proof generation is a must, and it could be very expensive. In OPML, we still have a challenge period, right? Just like any of the OP rollup that you might be familiar with. For machine learning, it might not be as long as 7 days, but there's still a challenge period that you have to go through. However, you can actually do what we call a fast confirmation, which is if you want to use the result yourself, which is what a lot of CEX is doing when you transfer anything from an OP rollup into a CEX, they actually do this fast confirmation, which is they run through the transaction themselves and they guarantee its correctness, right? If they do so, then they don't need to wait until the end of the challenge period. They can immediately consume that result as it is. Right, so, well, we have done a lot of this comparison in a lot of our previous talk, and what we have come to think about is, well, why can't we combine the two, right? Nothing stops us from combining the two. It's not true for rollups though, right? You cannot have a semi-OP, semi-CK rollup, but for machine learning, it's different. For machine learning, you can actually combine the two. You can have some part of optimistic machine learning and some part of CK machine learning. And that's what we call OPI. So optimistic privacy preserving AI. If you don't get this image, I would suggest you Google the word OPI, but I don't think it's very appropriate for me to explain what it actually means in Japanese. But yeah, so this is our attempt to basically take the best of both worlds. So we want to take the best of optimistic, we want to take the best of zero knowledge, and put them together. And we can do that because, well, a machine learning model can be broken down into many parts. Unlike a rollup, right? For a rollup, you need to do the whole thing in OP or you need to do the whole thing in ZK. But for machine learning models, I can do part of it in optimistic and part of it in ZK. So that's our proposal and the main theme of the presentation today, which is optimistic privacy-preserving AI on blockchain. And it comes from the observation from before that, well, first of all, we already established that ZK alone cannot guarantee input privacy, nor model privacy, due to the nature of machine learning itself. So actually, what we can do is, well, we only do ZK on the most important part of the model that we want to protect. And for the rest of the models, which is not that important, we will do optimistic system. So completely transparent, completely public, but we gain computational efficiency. So essentially what we do is we apply ZK selectively on different parts of the model, and we can save a lot of computation costs. So to, again, use maybe stable diffusion as an example, since I think a lot of people has probably played around with stable diffusion and have heard of fine-tuning. Right? So actually, when people talk about fine-tuning a AI model, it's only very small part of those model weights, right? So the model weights, it's like billions of model weights, but maybe only 100,000s of them are being changed by that fine-tuning, right? And stable diffusion itself is an open model. It's open by nature already. And it will be a waste of computation if we put it back to ZK and try to hide it. Right? So essentially, what you can do is you can just take those weights that have changed by your fine-tuning and put those into ZK. And everything that hasn't changed from the original open source stable diffusion, you put it outside of ZK. You only do it optimistically, right? Because you don't have anything to hide from, for those. So that you are basically only paying for the ZK cost of those weights that you're hiding. Right, so that's, I guess, like the gist of this optimistic privacy preserving on blockchain. Right now, particularly you can use it for fine-tuning. And I think one of the biggest advantage of OPI over any other methods right now is it can potentially bring size models of size that is probably unrealistic before, and put it on chain along with model privacy. So this is a very unique kind of gain that you get from using this scheme. Right. So what about products, right? How do we actually put this into real life? So from OPML into OPI, at Aura we do a lot of research. OPI is our latest research, but actually we have already put OPML, which is optimistic machine learning, into production. So which is actually what power our on-chain AI Oracle right now. So as I mentioned previously, we have stable diffusion and also Llama, right? Models that are of these huge size that we have never imagined in a blockchain, already currently available through our Oracle. So by saying that it's available on our Oracle, it means that you can basically write a function in your smart contract and request the result from our Oracle. And our Oracle will actually return that result to your smart contract through a callback. And one of the everything that comes together and realized as like a very key product of AI cross crypto is actually our initial model offering. So a lot of the times when we hear about people talking about AI cross crypto, a lot of people ask, what can AI do for blockchain, right? Why do we need AI on blockchain? And IMO, or initial model offering, is actually the opposite of the answer that we're trying to give you, which is what can blockchain do for crypto? So essentially, it's a way that we propose to use verifiable AI to be a source of funding or revenue for open source AI models. Yeah, so if anyone is interested, feel free to go on my link tree. So that my link tree will have the 2 preprints of the research that we have done. They're both on archive, as well as the different ERCs that we have written at Aura, and also, of course, the IMO idea that I've just presented. Thank you.